Okay, so for this section, we're going to talk about acid-base titrations. And the first thing I want to talk about are weak acid-base titrations, because strong acid-base titrations tend to be the easier ones to understand. So I have some images here that represent different places on the titration curve when we're talking about weak acids and strong base titration. So these images deal with weak acid with a strong base. Okay, so let's identify a couple of things here. So this is at the start of the titration. So before the titration even begins, we are down here at point A of our graph, okay? So a few things let's notice. We'll notice that we have a starting pH. So our pH is 2, which makes sense because we have an acid, so we would expect it to be lower than 7. And we have 0, we're on the 0 line because this is where we're going to be adding the base to our acid. So before the titration even begins, you're going to use, in order to solve for Ka, you can use the H plus concentration, or the pH, to find the H plus concentration, and then you should have the starting concentration of the weak acid. So therefore you can solve for the Ka. And you'll notice in this little bubble, so this little bubble is sort of blowing up what the beaker looks like at that point. So at point A, you have all of your HA molecules, okay? All right, so now the next point that we have on the graph, or point B, okay, or this area right here, this is referred to as the early buffering region, okay? So this is where you're going to start to see that weak acid do its buffer tendencies, okay? And we say that this is before half equivalence point, okay? We'll talk about what equivalence is here in a second, but before half equivalence, this is before when the buffering actually occurs. So at this point, to figure out the pH, you're going to be using that Henderson-Hasselbalch equation to figure out what your Ka is, okay? And at this point, our A minus, so our conjugate base of our weak acid, is going to be equal to the hydroxide that we have added into the solution thus far, okay? And you have the concentration of the weak acid that you start with, okay? Let's pause here and talk about what equivalence is. Equivalence is when you have the same volume of the acid that you start with and the base that you start with, okay? So this is before halfway to equivalence. All right, the next point, early buffering. So again, I think this is the same one. Oh no. You'll just notice that you're starting to form water molecules, which is making your pH go up, and you see your sodium ions and your conjugate base ions in solution. Okay, point C, halfway to equivalence. Okay, so you'll notice up here, this is the equivalence. So that is at, if you look, it's at around 15. So halfway to equivalence is about 7.5. So halfway to equivalence is when your pH is equal to the pKa of your weak acid. Why? Because the concentration of your conjugate base and the weak acid is 1. And you have to remember that log of 1 is 0. So the rest of that plus the log of the relationship between the conjugate base and the weak acid becomes 1. Or I'm sorry, becomes 0, so you can drop it off of the equation. So then pH is going to be equal to the pKa. Okay? So then after halfway equivalence, later buffering region, you're still going to use that pH is equal to the pKa. You're going to use that equation to figure out what the pH is or what the Ka is if you know what the pH is. Okay? And then you'll notice that your molecules start to drift away, your HA start to go away, and you're left with all of these conjugate bases. Okay? All right, point D, equivalence. Okay, now you'll notice for a weak acid and a strong base, the equivalence is greater than 7, okay? And the reason for this is you don't have enough H pluses at equivalence to consume the hydroxides from the strong base because they haven't dissociated all of the way, okay? So at equivalence for a weak acid, strong base reaction, you have to use Kb. Remember, we're above 7, which means we're now in our base zone. So we have to switch from Ka to Kb, and then we can solve for the OH concentration and then solve for the pH of the solution. Okay? And then beyond equivalence, you no longer can control the OH concentration. So now you're strictly just using that PaOH is equal to the negative log of OH, and then you can solve for the pH. Because now you have excess hydroxides present because you have gone past the equivalence zone. Okay? So, to summarize, this is sort of what a titration curve looks like. So you have before equivalence, so starting, okay? And then it shows you B is the buffering region, C is the halfway to equivalence, D is the equivalence, and then E is after the equivalence. And since it's a strong base, that's when you can use the POH equation to solve for pH. Okay, so how or when do we talk about this? Well, outside of doing an actual titration curve, to do this, we're going to do a sample problem where we're going to start with a weak acid, put or titrate in a strong base, and then figure out what the pH of the solution is based off of where we're at. Okay, so the question that I'm going to ask you is ultimately we're going to find the pH of a solution, okay? And I'm given 45.0 milliliters of 0.100 molar sodium hydroxide, and I'm also given 50 milliliters of a 0.100 molar acetic acid. Okay, now when I do this problem, I need to consider a couple of things here. Okay, first of all, the hydroxide from the sodium hydroxide is going to completely consume all of the hydrogens that it can from the weak acid. Okay, so we have to figure out if there is enough hydroxide to consume all of the weak acid H+, okay? So you have to remember that sodium hydroxide will dissociate completely into, sodium and hydroxide, where acetic acid will stay in equilibrium, and it'll be CH3COO- plus our H+, okay? So the first thing we need to do is figure out how many moles of hydroxide or acetic acid we have and how many moles of sodium hydroxide we have. So you have to remember that when you're given volume and molarity, you can solve for moles by saying moles is equal to volume times molarity. So in this case, I'm going to do 0.045 liters times my 0.100 molar, which is just going to move the decimal one more time. So it's 0.0045 moles of sodium hydroxide, where down here I'm going to have moles is equal to liters times molarity, which is equal to 0.050 liters times 0.100 moles. Molarity, which is equal to 0.0050 moles of acetic acid. Okay? So what that means is, if I have this many moles and this many moles, this 0.045 is going to consume 0.0045 moles of of acetic acid. Okay? Why? Because it's going to consume it to make water. Okay? So, with that being said, I can say 0.00, 0.50 moles of CH3COOH minus 0.0045 mole, and technically we're only talking about hydroxide. That is only going to give me 0.0005 moles of acetic acid left. Okay? So since I'm taking this away, okay, I am going to have left over conjugate base, because technically the only moles that's left here is the proton. Okay? The conjugate base will still be present because these two things in solution are going to make water. Okay? So ultimately, the reaction that you have is CH3COOH plus hydroxide, and you're making CH3COO minus plus water. Okay? So the hydroxide is stealing the proton from here. How much of it? 0.0045 of it, and making water. Okay? Since it's not taking all of it, that means I have some of the conjugate base left. I'm sorry. Whatever it takes from here is what I have for the conjugate base. So if I'm thinking about it in terms of a rice table, so initially I can say, okay, well I have 0.0050 here, and I'm talking about moles, and I have 0 here. If I add 0.0045 moles here, that means I'm going to take away 0.0045 moles here, because it's taking away the proton, okay, which means I have that 0.005 mole left here. I'm not going to have any of this, right, because it's not making hydroxide, it's taking the proton to make water, okay? But since water is not in an equilibrium expression, I start with 0 of this, and since I lost this from here, it had to make something without its proton, and that's its conjugate base. So then I have 0.0045 moles here. Okay? So far, I have enough information to now calculate the pH. Now to do that, I have to realize that I'm changing the volume, which means I'm changing the molarity. Okay? So I no longer have this in 50 milliliters. I started with 45 milliliters of the sodium hydroxide and 50 of the acetic acid. So I'm now talking about a 95 milliliter solution. So to solve for this molarity, I have to do 0.095 liters, which means my new molarity is 0.0053 molar. And then here, I have to do the same thing. My new molarity is 0.0474 molar. Okay? Now, I know this is a lot of work, I can use these molarities and the Ka that I was originally given. The Ka of acetic acid is equal to 1.8 times 10 to the negative 5th. I can do Ka is equal to H plus times the conjugate base, which is CH3 COO minus, divided by the starting acid. Okay, I have this, I have this, I have this. I can solve for H plus, and then I can solve for pH, and that is how you solve for if you add a strong base to a weak acid.